Hi everyone, welcome to another video, this time taking you through step 3 2020 question 2. Okay, I really like this question as far as step questions go. It's one of, in my opinion, the nicer ones, and I reckon I could have probably got maybe 17, 18 out of 20 in a decent time, as well as in 25 minutes, something like that. It's got lots of little bits to it. And I don't know actually, because I found out when I looked at the mark scheme that this was worth 6 marks, which I wasn't expecting. So maybe it would be slightly lower than that, I don't know, 16 out of 20. Because whilst I got the general shape of the curve absolutely right, I didn't realise the relevance of this point here, and although it was in the back of my head, like I should be using this result, but yeah, it didn't quite occur to me how it was useful. But yeah, so anyway, let's get on with it. So part 1. Show the curve C has equation sin x plus sin y equals 2k, where k is a positive constant. When I see something like this, I'm immediately thinking that's a symmetric function. Now, what's a symmetric function? It's one where if you swap x's and y's, you get exactly the same equation. Yeah, and what that always means is that it's self-inverse function, and therefore it's got reflective symmetry in the line y equals x. You want to be thinking about that straight away. That comes in really handy in part 3, when you're trying to sketch this thing. Anyway, let's get on with it. So, show that the curve has no stationary point. Well, naturally, we need to differentiate it. So, let's just start over here and shift the screen over a bit. So, I'm going to differentiate that. So, I'll just write it down first so we can see what I'm working with. Now, when I'm differentiating this, naturally, I'm thinking I'll need to use a little bit of implicit differentiation. K is a positive constant. That comes in handy later. So anyway, we get cos x plus cos y. I mean, let's face it, sin x and sin y are the easiest things to differentiate. Dy by dx, because we differentiated a function of y, equals 0. So that immediately leads to dy by dx is minus cos x over cos y. And if we assume there are stationary points, then we're going to set dy by dx equal to 0. We get 0 is minus cos x over cos y. So really that's just 0 equals minus cos x. Okay, so once I get to that point, at that point I think, well, this is fine, because actually cos x, if you think of the graph of cos x, it goes through 1, it never gets to the x-axis, does it? It looks very much like y equals x squared plus 1. And so if you're trying to solve cos x equals 0, you can simply argue, but cos x is greater than or equal to 1 for all x which are members of the reals, hence no stationary points. And that's like a mini proof by contradiction, isn't it? Because we assumed there was a stationary point and it led to a contradiction. Okay, that should be enough for that. We're not on part 2 yet. It's got like several different bits to it. Part 1. And d2y by dx equals 0 on this curve if and only if this is true. So, okay, we're going to differentiate again now. I chose to do this using quotient rule. So I just immediately went at this. Where's my pen? There we go. So I'm going to use this, and I'm going to use quotient rule on it. So I'm going to get d2y by dx squared equals, I like quotient rule, low d high, that's going to give me minus sin x cos y, minus high d low, well, that's going to give me plus cos x sin y. Oh, but I differentiated the low, in other words, a function of y, so I need to stick a dy by dx on the end. And then over the square of what's below. Now, we're going to set this equal to 0, and straight away, I hope you don't mind me just ignoring the cos squared y here. What I am going to have to do, though, is replace dy by dx with what it is, which is minus cos x over cos y. So I'm going to have minus sin x cos y plus cos x sin y, and then times by minus cos x over cos y. Seems natural here to times by cos y, and also to move this term over, and so that's going to give me sin x cos squared y equals, oh, I've missed out, look at that, that's bad, isn't it? I've missed out a little argument here, that should have an x on it, equals cos squared x minus cos squared x sin y. Okay, so there we go, lovely looking result here. Now you might think, well, how am I going to get to this? Well, the first thing you notice is it's all in terms of sin, So it seems once again natural to replace cosh squared with 1 plus sine squared, because remember that cosh squared A minus sine squared A is equal to 1. You can use Osborne's rule there to make it to go from sine squared plus cos squared plus sine squared as 1. Osborne's rule is very handy. Okay, so cosh squared y is 1 plus sine squared y. And likewise here, I'm going to change that into 1 plus sine squared x, sine y. And then I'm going to see what I've got by putting it all on one side and making it all positive. Well, I've got sine x plus sine squared y plus sine y plus, oh, did I say sine squared? Sine cubed, beg your pardon. Oh, and hang on, sorry, this is a, let's get this right, I'm messing this up. Okay, I'm going to have sine x, and let's write it in a nice order actually. Can you see I'm going to have plus sine y there? But then I'm going to have plus sine x sine squared y plus sine y sine squared x after I've added it over. And that equals 0. And now if we just do a little bit of factorising, we've got sine x plus sine y plus, now look at these, they've both got sine x and sine y in them. And then we're going to need to multiply this by sine x plus sine y. And we can of course factorise this, look at that, because they've both got a sine x plus sine y in them, to give us sine x plus sine y multiplied by 1 plus sine x sine y equals 0. Now, you might think, oh, well then there's two ways of getting second derivative equal to 0. We could either have sine x equals minus sine y, or 1 plus sine x sine y equals 0. Now, they said there was only one. They said if and only if this is the case. So this is the case, then that's the case, and if that's the case, then that's the only case, because that's the way an if and only if statement works. That's the way implication works in maths. But if you look carefully at the original result, you can say, but if sine x equals minus sine y, then sine x plus sine y equals 0. And this is not possible, as k was defined to be a positive constant. Yeah? K is a positive constant, and 0 is not a positive constant. Hence, 1 plus sine x sine y equals 0 is the only way of getting the second derivative, given the conditions that we were given in the question. Second derivative equal to 0. Okay, so we've done that. Find the coordinates of the points of inflection on the curve C, leaving your answers in terms of inverse hyperbolic functions. Sure, so we've got a second derivative is where the, points of inflection are where the second derivative equals 0. So let's go with that. Especially when the first derivative doesn't equal 0, that shows it's a non-stationary point of inflection. Okay, so that's what we've got here. So we're going to try and solve this. And let me go underneath here. So we're going to oh, actually no, I'll leave that space for when we do part 2 later. So we're going to solve, and we're going to get sine x is minus 1 over sine y. Yeah, that's a condition on which we will have a non-stationary point of inflection. And if we use our original equation all the way up here, sine x plus sine y is 2k, we'll be able to replace sine x with minus 1 over sine y plus the sine y equals 2k, and we'll be able to solve this and find our solutions in terms of k. And so I'm going to times everything by sine y. And this is of course a quadratic in terms of sine. So we get sine squared y minus 2k sine y minus 1. Personally I solved it by completing the square. So half the coefficient of the middle term, if you like. Square it, and then we've got minus k squared minus 1. And so sine y, if we undo all of that, is going to be k plus or minus the root of k squared plus 1. And so y is r shine of all of that. And I think they asked us to leave our answers in terms of inverse hyperbolic functions, so that is. There we go. Okay, now what is x? Well, remember earlier I said it was a symmetric function, which means that when y takes one value, x takes the corresponding value. They should just really swap over. But I suppose a really easy way of getting the answer is to just look at this and say, well, shine x plus shine y was supposed to be equal to 2k, and shine y is this, yeah? So shine x just equals 2k minus what shine y is, which is k plus or minus root k squared plus 1. And so that's going to immediately give me 2k minus k, and then the plus is going to change to a minus, and the minus is going to change to a plus. So we get minus plus root k squared plus 1. In other words, when shine y is the plus, shine x is the minus, and when shine y is a minus, shine x is a plus. So our corresponding x values are x equals r shine. Had to have the same answer but just switched, basically, because it's a symmetric function. Yeah, the x's and y's just swap over. Okay, so there we go. Okay, we're on part 2 now, and I'm hurrying a little bit because my dinner's almost ready. Oh, I've heard a tap on the window. My dinner is ready. Okay, show that if xy lies on the curve C and on the line x plus y equals a, then you get this. Well, this wasn't too difficult either. It definitely didn't escalate really here. The sketching at the end is tricky, but I didn't think this was too bad at all. Okay, so we've got x plus y equals a, and shine x plus shine y is 2k. So I'm just going to do what you'd guess, which is I'm going to plug in, especially as this is all in terms of x, I'm going to plug in y as a minus x. So I get shine x plus shine of a minus x is 2k. They've got exponentials involved, so I'll use the exponential form. E to the x minus e to the minus x over 2 plus e to the a minus x minus e to the, well, a negative of that is x minus a all over 2 equals 2k. Times everything by 2, you get e to the x minus e to the minus x plus e to the a minus x minus e to x minus a equals 4k. That's looking good. We probably should have times by e to the x as well, because they've got 4k e to the x involved, so that's the little hint, isn't it? That will give me e to the 2x, so I'm timesing everything by e to the x, minus e to the 0, well that's 1, plus e to the, well, it's just going to be e to the a, and then this is going to be e to the 2x minus a, and that equals 4k e to the x. And from here I think we can go to the answer, because we've got an e to the 2x, and then an e to the 2x times by e to the minus a. That's that term and that term dealt with. Then we've got a minus 1, and we've got an e to the a, and then we've got a minus 4k e to the x in the middle. So we've got exactly the answer we wanted, and it equals 0. Okay, hence deduce that 1 is less than cosh a, which is less than or equal to 2 squared plus 1. 2k squared plus 1. Okay, well, my immediate thought here was, how do you start with what's a quadratic equation, but in e to the x, a quadratic in e to the x? How do you end up with an inequality? Well, discriminant seems like a good idea, because if we want this to have real solutions, i.e. that point genuinely does lie on that line, then we can say the discriminant of this is greater than or equal to 0. So that's what the principle I'm going to use. And this is all standard stuff, especially in STEP, standard stuff. So 16k squared, b squared, minus 4 times by a, well it's this one, times by c, that's that one, equals, oh, not equals, but is greater than or equal to 0. That's our discriminant. Divide it all by 4 and times out the brackets. You're going to get e to the a, and then you're going to get, now let's get this done very, very carefully. You're going to get minus e to the 0, minus 1, and then you're going to get, when you times, you've done that by that, plus e to the minus a. It's greater than or equal to 0. And what is this? This is 4k squared minus e to the a plus e to the minus a minus 2. Yeah, and that's from that term and that term. That's your minus 2. And that is 2 cosh a, isn't it? And so we get 4k squared minus 2 cosh a minus 2. And therefore, after you've added the 2 cosh a onto that side and halved everything, you're going to have 2k squared plus 1 on this side, and cosh a is less than or equal to 2k squared plus 1. So that's sorted out half the inequality. Now, why can't it be equal to 0? Because cosh a obviously is always greater than or equal to 1, and that's just from the fact that on a cosh graph it's greater than or equal to 1 always, yeah? So why is it greater than 1? So I merely argued like this. I said, if cosh a equals 1, yeah, so let's just say cosh a is greater than or equal to 1 for all a, which remember are real numbers. But if cosh a equals 1, then a equals 0, in which case, remember, x plus y equals a. So I'm just going to say then x equals minus y, but then shine x plus shine y equals shine x minus shine x, and that's because shine is an odd function, just like sine. Yeah, shine of minus x is minus shine of x. Yeah, and you definitely want to know that. Yeah, and use that all the time. They constantly test it. Yeah. So yeah, that's just because it's an odd function, and that equals 0, but k is greater than 0. Yeah, and hence we've got our inequality now. Hence 1 is less than cosh a, which is less than or equal to 2k squared plus 1. Yeah. Now, sketch the curve C. Okay, this is where we put it all together. And like I say, it was worth 3 marks. Now, first thing I thought is I know it's got reflective symmetry in y equals x. That's a big hint. Yeah, right, in y equals x. I also thought as x tends to infinity, y must tend to negative infinity. Yeah, and that's just because, you know, when these values, firstly, shine just gets bigger and bigger and bigger. Think of the graph as you get bigger and bigger and bigger. As x tends to infinity, y tends to infinity. So if you're doing shine x minus shine y equals, just a pesky little constant, a tiny little number, well, shine y needs to get super large as shine x as shine x gets super large, just because the difference is only a constant. And so I figured that first, and likewise, as x tends to negative infinity, y tends to positive infinity. Yeah. So this gave me some ideas about how to draw it, because I thought immediately it's going to start from top of this quadrant and end up down here somewhere. We know it's got a point of inflection on the negative side and on the positive side, yeah, because we found the coordinates of those. They were, where were they? Where were they? Here we go. X is r shine k plus or minus, and y is r shine k plus, yeah? So one's negative when the other one's positive. Have a little think about that and you'll see one's negative when the other one's positive. So we're going to get a point of inflection here, yeah? We can also find, by the way, the coordinates here and here really easily, because remember that shine x plus shine y equals 2k. So if you let x 0, you can see y is going to be r shine of 2k. And likewise for the other one. That's also going to be r shine of 2k, but just on the x-axis instead. Sorry about my terrible diagram here, this is difficult for me. Now, I also knew that the POI is the points of inflection. Let me just get that drawn nicer. Oh, I've ruined it. I also know for the points of inflection, which you really should put on your diagram, I'd actually label them, where a curve inflects, aren't they? I'd actually label them like this. I'll just put the red over here, and I'll just put point of inflection. And I'll put the coordinates next to it, x equals, I think I had it down as r shine k minus or plus k squared plus 1 y equals, you know, I do want to put that on my diagram because I'm sure that'll be worth marks. I'll have to check the mark scheme again to see how many, and I've already worked it out, so I might as well use it. Now, what you're also supposed to realise is this last result that you've proved is actually showing you the values which the curve is trapped between, yeah? Because, where are we, yeah? If you look at this, we know xy lies on the curve, and it, you know, and on the line x plus y equals a. We also know as well, the reason why I've drawn it like this is because remember, it's got reflective symmetry in y equals x because it's a symmetric function. Well, it's actually trapped between the line x plus y equals 0, and that's because that's where a is 0, and if a is 0, well, you get cosh a. We've already worked out this condition, haven't we? If a is 0, then you get like cosh of 0 is 1, but we know that this is going to be bigger than that, the cosh a value, and so, you know, this is lovely. This is telling us the range of values between which the curve must sit. And so the final line is going to be coming down like here, and that's going to be literally r shine. Just quickly write that down. X plus y equals, well, this is the a value, isn't it? And the a value here is cosh, sorry, 2k squared plus 1, yeah? We know the curve is going to be trapped between those values. Okay, and that's, yeah, that's probably a bit which I would have missed at the end, but yeah, done all the algebra. But it's worth 6 marks the graph, so they did want it done nicely. Okay, hope that helps, and Dylan, if you're watching this, good luck in the exam. I hope you can see that this one's quite a nice one. Okay, all the best and keep up the hard work. Bye bye.